An implementation of a differential amplifier is shown in this circuit design example. We have two voltages V1 and V2 at the input of the circuit, and then we have voltage Vout at the output. We want to prove that Vout is proportional to the delta or difference between the two input voltages, and the coefficient or scale is 1 plus 2 over 3 alpha. Basically, Vout is 1 plus 2 over 3 alpha times V1 minus V2, in which alpha is the coefficient of the two resistors at the input and output of the circuit. Okay, so for quick analysis, as usual, we make the assumption that the op-amps, both op-amps in this circuit, properly biased. The circuit is implemented with two operational amplifiers. And because for both op-amps we have negative feedback because output is connected via the circuit elements, as you can see, to negative input terminal or inverting terminal. Therefore, we can assume that these two op-amps, op-amp 1 and 2, are operating in linear region. Therefore, voltage at positive terminal should be equal to the voltage at negative terminal, which we refer to as known virtual short. So virtual short is valid for both op-amps. Now, when V1 is applied to the input positive terminal, there is no current going through this resistor, so 0 milliamp or microamp. Therefore, V1 is exactly at positive terminal. Virtual short via the negative, in fact, enforces that we have V1 also at negative terminal. So again, because no current can go through the input terminal of op-amp, so there is 0 milliamp going here. Therefore, V1 is exactly at this node as well. Now we can compute the current that is going through the alpha R resistor. Because there is a voltage drop V1 across alpha R, we can say this current, which refers to as I1, is simply V1 divided by alpha R. So let's refer to this as equation 1 here. So let's have it as equation 1. Now, this current can only go through this resistor as well, so we can compute the voltage at this node, therefore. So if that is, let's say, voltage, let's refer to it as voltage V3, as an intermediate voltage, I can say V3 is equal to simply V1 plus the new voltage drop across resistor R, so VR, and VR is simply just the current I1 times R. So I'm going to just substitute for these. So V1 plus V1 over alpha R, that's the value of current as from equation 1. And then we have times R, so therefore the outcome becomes V1 times 1 plus 1 over alpha. So this is the value of voltage for V2. So we found V2 for V3. So we found the V3 to be V1 times 1 plus 1 over alpha. Now, what happens is we have two currents. So we have a steel current I1 that is passing through our resistor here, as we just discussed. And then we have current I2 here as well, that is now going through R. The sum of these two currents is passing through this resistor because of KCL at, or Kirchhoff current law, as at this node. So the sum of outgoing current should be equal to the incoming current. So therefore, I just use that, and I'm going to write that voltage at the output of op-amp 1, or Vout1, which is exactly this node. So Vout1 is equal to, we have V3, so this voltage, plus the voltage drop across this resistor, which is simply the I1 plus I2 times resistor R. So I am going to say V3 plus R times I1 plus I2. Now I'm going to substitute for these currents. So I have, let's refer to this one as equation 2, the one that defines V3. So I'm going to use equation 2 to substitute for V3. And therefore I have V1 times 1 plus 1 over alpha plus R times, and substituting for I1 from equation 1, I have V1 over alpha R. So that's substitution for I1. And then I have also, again, R, this R, times I2, but instead of I2, I'm going to substitute simply V3 divided by R. So it will be V3 divided by R, and we have the value of V3, so it will be V3, which is from equation 2, V1 times 1 plus 1 over alpha. So what happens is now we have, as you can see, because of this whole thing here, if we just simplify the values, basically R cancel out with R cancel out with R, and then what we get as a result of this whole thing, we get 2v1, or basically just simplify 2 plus 3 over alpha times v1. So this is the value of voltage at the output of op-amp 1. So let's refer to this as equation 4. So we found the voltage here as Vout1, which is shown in equation 4. Now, we can focus on the second stage because this circuit effectively has two stages. So second stage is this stage. As you can see, we have effectively two voltages applied to the second stage. One, we have voltage V2 at the input of at the non-inverting or positive input terminal. And then we have voltage VO1, which is coming from the first stage and applied to this, let's say, network of ladder resistor. And then we have connection to the negative or inverting terminal. So what I can use superposition now. So reason for that is, of course, I can use the combination using, again, the circuit laws, but superposition has the benefit of making things a little bit simpler. So, for example, let's say using superposition, meaning that I'm going to consider these two voltages one at a time. So superposition, I'm going to assume that for now, for example, voltage V2 is 0. So using superposition, assume V2 is not there. So V2 is 0. So we only have VO1 coming from the first stage. So the circuit looks like this. If we are grounding, basically assuming V2 is not there, it means we are grounding it. So we are assuming it's just grounded, shorted. That means the positive terminal is grounded. And because of virtual short, so we know that op-amp is operating in linear region, and with negative feedback, which enforces that the voltage at positive negative terminal for op-amp 2 is the same. So when positive terminal is grounded, it means negative terminal is also grounded, which is virtual ground. So this node, again, because no current can go through op-amp through resistor R, therefore this node is also 0 volt at virtual ground. So what's the benefit of that? The benefit is both resistor R here is grounded on one side and resistor R shown here grounded on one side. So effectively these two resistors are in parallel. So the circuit becomes as simple as this scheme with V2 0. I'm going to show it here. So circuit becomes R, we have Vout1 from the first stage. Effectively we have, from perspective of Vout1, what we see is the parallel of two resistors, which is R and R, both effectively grounded, so 0 volt. So this is observed as simply R plus R over 2, because that's the effect of R and R in parallel, which becomes half of R. So the sum of these becomes effectively, what I'm going to show is effectively Vout1 thinks or notices or observe as if we have a 3R over 2 resistor connecting to the negative terminal of op-amp number 2, that positive terminal is grounded when we are saying V2 is not there. And then alpha R is still there. So we have alpha R. And then connected to the output of op-amp 2, which is the output of the circuit. Okay, so this is now looks like actually very simple to calculate, because now we can say the current that is injected to the circuit, so I'm going to use a different color so that it is clear. So the circuit, the current that is injected through the circuit, let's say I3, because I have used I1 and I2 before. I3 is simply calculated like this. I3 is equal to Vout1 divided by 3R over 2. That's the resistor observed from Vout1 to ground. But then not all of these current is going to the output of the circuit. Half of it, when it gets to this node, because of KCL and because we have two equal resistors connected to ground, half of I3 goes to this resistor, and the other half is the one that matters to us. So the other half is the one that is going to the output of the circuit. And since no current can go through the input of op-amp because of effective infinite impedance, then I3 over 2 is the one that keeps going through the output of the circuit to resistor alpha R. So given that 0 volt is on one side of alpha R, then we can compute the output because of voltage drop across alpha R. So I can say with this, V out is simply half of I3 and a negative voltage drop. So half of I3, negative voltage drop across alpha R. So substituting for I3 from this equation that we have, we can say contribution of the voltage coming from the first stage when V2 is absent is simply then minus 1 over 2 V out 1 3 R over 2 alpha R. So I just substituted for I over 3 from this equation. And as a result of that, we can see R cancel, 2 cancel, and they so basically we just get minus alpha over 3 V out 1. That is the value for, let's say, the voltage V out. But then I can use equation 4 here. So I'm going to use then equation 4. So that I'm going to substitute for V out 1 from equation 4. And then I'm going to define V out as a function of contribution from V1, which is the only active voltage in the circuit because we assume V2 is not there in the superposition. So we get V out is equal to minus alpha over 3 times then this one instead of for V out 1, I am using equation 4. So it means I'm substituting it with this value. So 2 plus 3 over alpha V1. And obviously when I multiply this, I get this. I get V out equal to minus 1 plus 2 alpha over 3 times V1. Okay, so let's keep this as equation 5 because this is not yet done in terms of complete analysis. We are just done with understanding and computing that when V1 is there, how it impacts the output of the circuit. So we found it. Now let's do the other way. Let's continue the superposition. So the next step of superposition is assume. So the first step was assume V2 is 0. The next step is assume. So for again superposition, assume now V1 is 0. Again, there are many ways to do the circuit analysis. This is one of the methods. Okay, if we do that, then now V2 is there connected to the positive terminal, but then V1 is 0 as if we have here at the input of the circuit, V1 is grounded. If V1 is grounded, it means there is nothing coming from this portion of the circuit. So effectively, we have, because we are shorting V1, at the output of op amp 1, V out 1 is 0 enforced. So it would be ground here. And therefore, because when V1 is grounded, there is no current going through this portion of the circuit, there is no voltage drop, and therefore we are connected to this node, which means we have ground, or let's say 0 volt at this node, at V out. So I'm going to use that. Therefore, the circuit equivalent becomes something like this. So as I said, at the output of, so V out 1, or output of op amp 1 is effectively grounded. We have resistor R, we have resistor R, we have resistor R, and we have connection to the negative input terminal of op amp 2, where positive terminal via resistor R is connected to V2, and then we have alpha R resistor in the feedback loop of op amp 2. So output of the circuit now can be computed, which means we are finding the contribution of V2 to the output of the circuit. Again, this is easy because this is exactly the look of a non-inverting amplifier, contrary to the previous one that looks like an inverting amplifier. So in the non-inverting amplifier, it becomes as simple as this. We have R parallel with R, so that would be R over 2. So the circuit effectively is equivalent to, say, R over 2 in series with R connected to the negative terminal, then inverting terminal of the op amp, let's say number 2, where we don't care about this resistor because input of the op amp has infinite impedance, so no current can go through this guy. So V2 is connected directly to positive terminal, so therefore I can just show that V2 is effectively at positive terminal, and then we have alpha R and output of the circuit. This is a non-inverting amplifier. I can just quickly write the outcome, but just to show you quickly. So because of virtual short that is enforced by negative feedback, V2 has to be at negative terminal as well. So both positive, negative has to have, they're supposed to have the same voltages, the same voltage. Now, because of this V2 across this 3R/2 resistor, we have a current flowing through them, and that current can only go this way. So therefore, we can say V out is simply V2 plus that current, which is V2 divided by this resistor, which is 3R/2 times the alpha R that this current is flowing through and result in additional voltage drop that adds to V2 to give us V out. So therefore, we get times alpha R. This is exactly the gain of the non-inverting amplifier. So if I factor out V2, I get V2 plus 2 alpha. So obviously you can see that R and R cancel out. They cancel out, and then we get 2 alpha divided by 3. Okay, this is equal. So we found the contribution of, so let me show it this way. So one more time repeating V out so that I have it. There you go. Okay, so we found that therefore V out is this one, which we refer to it as, say, equation number 6. Combining equation 5 and 6, the two contribution of V1 and V2 to output voltage, then we get the final result because these are the outcomes of superposition. So now combining them together, so I would say combining or adding equations 5 and 6, we get V out overall equal to this plus this one. So since the multiplier, keep in mind the negative sign here, but since the coefficient is the same for both of them in terms of multiplying V1 and also V2, so it's 1 plus 2 alpha over 3. I'm going to factor that out. So 1 plus 2 alpha over 3. And then we have obviously V2 minus and V1. So therefore we get V2 minus V1. This is exactly what we wanted to prove for the gain of this differential amplifier that basically computes the delta or difference between the two input voltages like instrumentation amplifier, and then multiply that by a gain that can be controlled by what we set as the resistor here, alpha R and alpha R. So for instance, if we set alpha to say 90R as an example, so if as an example we set alpha to 90, so become 90R, then we have, so if alpha is 90, then we get obviously V out equal to 61 times V2 minus V1. That's an example. So sometimes this circuit is referred to as differential input instrumentation amplifier effectively, because the two inputs, the way they are connected to the positive terminal of op amp, it's not, there is no current being drawn effectively from the inputs, and therefore we can use this for, let's say, if there is a sensor connected between these two nodes in a differential fashion, we can basically get the signal from the sensor or voltage and then have a gain for that in a differential amplifier fashion. I hope that this example is helpful in terms of showing an implementation of the differential input instrumentation amplifier.